Good morning, everyone. I'm Pressure-Fed Astronaut. This is End of Mission, the podcast where we talk about missions that have ended. Why are you in my house?
What? I'm not in your house, dude. I'm in my own pad, my apartment. I'm on the other side of the friggin' continent, man.
Then why are you on my screen? If you're not in my house, why aren't you on my screen, huh?
Okay. We're gonna have a conversation about how technology works a little bit later. I'm face of sarcasm. I'm some guy, just a random dude that stumbled upon this.
Yeah, you stumbled into my house. And now we're going to learn about
Yes.
space missions.
Yeah. Why do you have me in chains in my own abode?
It's my house. You broke in. Okay.
Oh, okay.
Okay. Yeah.
I don't understand the logistics of this joke. It doesn't make any sense.
Neither do you. So let's just get going. Okay.
Okay.
Do I have anything custodial to talk about? Oh, okay. I hate to do this, but I normally don't say this because, I figured if you found me, you know how YouTube's works, right? But I would like it if some of you would, smash that like button very inappropriately, and subscribe, comment, evangelize even the good word.
Wait, are you being corrupted by the YouTube algorithm? Are you now feigning enthusiasm and saying like, "Hey, please like, share, comment, and subscribe. Tell your friends about it. Donate to a Patreon that doesn't exist."
I am going to do a Mr. Beast face on this thumbnail for this.
Okay. Well, I mean, I'm making the thumbnail, so
let's do your face as you're screaming, "Why am I in your house?"
Yeah. Why am I? Yeah, it's gonna be me tied up to the chair, and
Yeah.
I'm gonna somehow take a picture of that because I live alone.
Yeah, in my house that you broke into.
Yes.
Because I understand things.
Uh-huh.
Yeah. Oh, and I just remembered this. This is something exciting. The Osiris Rex mission tomorrow morning, 9 a.m. Central Time. Okay, well, yesterday morning when this is uploaded on Monday, we'll have its sample return, which is why we're not talking about the sample return mission that didn't work, Genesis.
Oh.
Yeah.
Oh. No, that would be very on point.
Yeah, but
Yeah,
but that
very topical.
would require me, hitting schedules and deadlines.
Oh,
Instead,
yeah, that makes sense.
Instead, we're going to talk about some technology.
Technology?
Deep Space One.
Deep Space Nine.
No, Deep
Got
Space
it.
One. This isn't Star Trek, buddy.
Dang
This
it.
is the prequel. I mean, look at this. Does that look like Terok Nor to you? Do you see any Ferengi
I have
in
no
this?
idea what that
That's
is.
the Bajoran name for Deep Space Nine.
I just call it Deep Space Nine. Why do you gotta add all these different names to it? It doesn't make
true.
any sense.
What do you think this mission's about?
Well, judging by the incredible cover art of this beautiful satellite and probe visiting what looks to be like a comet or a very emissive asteroid, I'm guessing it's about the manned missions to the moon.
Yes.
Yes!
Actually,
Nailed it!
This is like a disco nightclub kind of thing, right? It's got the lights going. It's got the DJ. This is just going,
Yeah, that's the cops coming around saying like, "Hey, keep the noise down. The neighbors are complaining."
Yeah.
Because noise travels through space.
So this mission actually happened about 20 years ago.
To the date, or
Not to the
just
date,
like
no.
in general?
Actually, close to the date.
Ooh.
Yeah. Okay, so
Okay.
we have to do some background on this. Okay.
Oh God, math.
Yeah. So you see that top equation here? This one, number
Yeah.
1? That is...
Yeah, I see the math number with no numbers.
Yeah. So this is called the Soislavsky... I can't speak Russian, okay? The only
Zuzlewski.
Yeah. That equation. It's the rocket equation. It's the one that controls all of our lives if you're an aerospace engineer who likes rockets, right? Delta V equals exhaust velocity times the natural log of MO over MF. That MF, right?
Them MFers.
Right. So it's kind of like miles per gallon, right? But in space, you have delta V, which is your change in velocity, right? You go
Okay.
fast to go high, right?
Go fast to get high.
Yeah.
To get high, to go fast.
With Vin Diesel.
I'm speed.
Yeah. Right. So that's the equation that controls how rockets are sized, where you can go, what you can do with them.
I'm sure someone understands that.
Yeah. No one on this channel, of course, because I don't talk about this at all, ever.
Okay, good.
Yeah.
Good.
And then the other equation that's way crustier, this one. So that's the equation for this guy. VE, exhaust velocity. See, that's VE. Now,
Yeah.
you're going to see it's big and scary, but there's a few things that we can control for, such as...
Oh, look, numbers.
Yeah, you have 2
If 1.
and a 1.
Yeah.
So that's PE, so that's physical education. So if you work out more, you're going to go faster, right?
Got it.
So that's the
Got it.
exit. Is that... I can't tell... Okay, I haven't... I think that's the exit pressure of your engine and then pressure of the chamber. You can control your chamber pressure, right? Because how fast you go, how fast you can change is dependent on how much propellant you can carry and how fast your exit velocity is, right?
Okay.
And then, so exit velocity is controlled by a few things, like temperature and the molecular weight of your combustion products. R is what this is rated. That's a gas constant. You can ignore that.
I thought this was a good Christian channel.
That's true. It is.
Unbelievable.
Where's the fish? I can draw a fish on here for you.
Please don't.
Okay, PFA here in the editing bay. Figure I should really explain the rocket equation a bit better. Okay, so the rocket equation, delta V, your change in velocity, equals exit velocity times the natural log of the mass ratio. Pretty much what this means is it's kind of that, Newton's laws thing where, to change velocity, you got to add velocity. Well, the total change in velocity a rocket can get is related to the exit velocity of the combustion products, which, right, you're burning fuel and oxidizer, and then the natural log of the mass ratio. The mass ratio, of course, is the ratio of how much you weigh at the beginning of the burn versus how much you weigh at the end of the burn. And then exit velocity is determined by this really icky equation. The few things that you can control in there are the ratio of the chamber pressure versus the exit pressure. That's the ratio of P. The temperature of the combustion, and then the molecular weight of the combustion products. So for what we're talking about here, so for ISP, that's your exit velocity divided by gravity, so it's usually measured in seconds. You're kind of limited what you can do, right? For chemical propulsion, like this. This is the Cassini space probe, that one that went to Saturn. So these
cool.
So this uses storable propellants and had, I think, 2 kilometers a second delta V. This thing didn't weigh much. I mean, weighed 5 tons, I think. I don't remember.
So it had storables as opposed to homemade.
Yeah, store-bought versus homemade.
Got it.
Homebrew.
Got it.
Yeah. The problem is with standard chemical liquid bipropellant engines, you can only really get up to about 460-second specific impulse using liquid hydrogen and liquid oxygen.
Okay.
Which is
that
not
good?
Well, it's good if you're not going to spend a lot of time in space, because then it's going to boil.
Oh, okay.
That's a problem. So normally we use storables like NTO and MMH, which cap out about 320 seconds specific impulse.
Okay, I know what those letters mean.
Yeah.
Yeah.
That's dinitrogen tetroxide and monomethylhydrazine.
Of course, I just told you. I know exactly what those letters mean.
Yeah, nerve agent and cancer.
Yeah.
So one alternative that was proposed for human space flight, specifically for Mars missions, is nuclear thermal propulsion, which would run liquid hydrogen over a nuclear reactor.
Oh, okay, so it has a bunch of spicy rocks to make it go fast.
Yeah, because, sure, there's limitations to this ratio, the pressure ratio of your engine, but your molecular weight you can control, sort of, and then temperature is what you can control, right?
Oh, so you make it, like, real hot.
Yeah. Well, again, there's still practical limitations to that. So that's why nuclear thermals would always use nuclear reactor, which can get hot naturally without anything else, because it's,
Spicy rocks.
it's radioactive. And then the molecular weight of hydrogen is 2.
Yeah, that's pretty small, right?
Which is really small, which means you can get your exit velocity up to about 900 seconds.
Oh, that's more than the 460 you mentioned earlier.
A lot more.
That's better then, right?
Yeah. The only problem is that you're flying a nuclear reactor into space.
I see this as an absolute win.
I see it as a win, too. The Soviets saw that, too.
Yeah,
We have to talk
all right,
about-
we're all in agreement then.
We have to talk about
with
Rorschach.
NERVA?
No, of course not. The other problem
Dang
is,
it.
look at how big that thing is, right? Want to do space probes? That's not as... You're not going to get a thing out of that. So there's an alternative. They're called ion engines.
Ooh, okay.
Yeah.
What does that mean?
I don't know.
Oh,
So pretty much what it is you take a propellant atom, right? See, that guy. That's a propellant atom. And you
It's pretty
throw...
big.
Yeah, you throw... It's really... Yeah, its engines are really small,
Ah, okay.
Or it's just really fat atoms. It's an American, kind of thing.
An American atom.
Yeah. And you throw
Easy to split that guy,
Right? And you throw electrons at it. You put in a giant magnetic
Okay.
field, and then it strips away some of the electrons. I think So you turn it into a positively charged ion, right? It's really happy.
Okay.
So it's going to put a little smiley face in. It's really happy. It's a positively charged ion. And you use electromagnetic forces, electricity, and then you put it across this gridded thruster thingy, which is positive here by 1,090 volts, right? That's what it says.
Okay.
That's a thought. Yeah, this is originally what I had.
You have black text on a dark gray
This
background.
is the one diagram I got from this mission, and it doesn't have easy to read text boxes. And then
You have access to Photoshop. You could have just gone in and brightened it up.
Do I look like
Could
I
have
know how to,
recolored those letters.
Do I look like I know how to do that?
Oh, yeah, that's right.
I use a stepladder to record videos. I don't even have a tripod.
Yeah, I only design rockets as a hobby.
Yeah. So you have this massive voltage difference, which is potential. That's what voltage is. And it takes those positive ions and it throws them out the back really fast.
Wait a minute. So this electromagnetically accelerates atoms that are charged based off of that are charged from these electrons being fired at them.
Yes.
Then they get passed through this electromagnet, and then they have the ions stripped away from this electron gun at the end.
Yeah. Well, then at the end here, so it'll throw some electrons in for fun.
Okay.
It's like T-shirts, right? It's like here, take this back
Right. Okay.
to neutralize it. That's what it says
Neutral.
there. Yeah.
Okay.
So it just throws
So-
ions out. Now, the best part is these ions go out really fast because they're just
How
atoms. Let's see. So your specific impulse, specific to this engine, the next thruster, or no, not next, N star. Next is another one. From 1,660 seconds to 4,190 seconds.
So like almost 10 times the chemical rockets.
Yes. So let's see. What's the upsides to this kind of propulsion? Okay, so you don't need as much propellant, right? Your ISP is really high,
Yeah.
which means you need less propellant to make it go.
Okay.
The propellants aren't toxic. Xenon's great. It's fun. It's really expensive, though. Argon, krypton, right? You got a bunch of those. The exhaust looks really cool. It's that glowing stuff, right? It glows blue,
okay.
right? You played Kerbal Space Program, that blue glow, that's xenon, right?
Ooh, okay.
So here's some downsides. The biggest one here is it's got very low thrust.
Like how low?
You sneeze with greater force than these engines.
Oh. Is that because they're just like breathing atoms out as opposed to like, fire that the chemical engines do?
Yeah. Because when it's hot gases, they want to get out.
Okay.
With ion engines, it's just keeps throwing them out.
Okay.
Yeah. So that, because it's got low thrust, it needs longer duration burns, which means you need higher mission delta V. For example, when I did Cletus, my propellant resupply architecture, back several years ago now, we used argon-powered ion thrusters to get from low Earth orbit to the moon for my 145-ton tanker.
Jeez.
That took 2.5 years.
Just a casual stroll around the Van Allen belts there.
Yeah, you hang out there, chilling. Yeah, so your delta V goes from 3.2 kilometers a second to 6 or
Got
7.
it.
But it's more efficient in trade studies, right?
Okay. I'm sure it is.
It's power hungry, obviously. So these ion thrusters need about 2.3 kilowatts power to operate.
How much is that compared to like how much a home uses?
I don't know. I didn't think about that. That was a question.
Okay. Is that like a lot? Is that like a little?
Let's see.
How many car batteries gets you 2.3 kilowatts?
The ISS solar arrays operate beginning of life at about 150 kilowatts.
Okay.
Yeah.
So you don't need a whole lot then to power.
It depends on your mission, of course. And you get high thrust, low thrust.
Okay.
We need solar arrays, or once you go out past Mars or the asteroid belt, you need you need nuclear reactors to power it. Versus chemical propulsion, which is you need a spark igniter or hypergalls, and you just need to push them in.
You just need a really brave Russian with a Zippo lighter.
Yeah. So it's power hungry. It could be an issue, right? And then gridded ion thrusters like this one, they will erode over time.
Oh,
Now, when I say over time, we're talking 15 years of firing.
like constantly firing?
Yeah. Actually, at I think Glenn Research Center, the one in Ohio, for a while they just had an ion thruster firing in a vacuum chamber for several years.
Just to see what would happen?
Yeah. They just kept running for several years.
Man, what are they doing in Ohio?
They're trying to get out. But the problem is
Yeah,
ion
yeah.
thrusters don't have much thrust. So the common propellants we see on ion engines, xenon's the big one, argon, krypton, mercury, iodine, cesium, bismuth, and Teflon. Though others have been proposed because it's just ions, right?
So just all the propellants with the coolest names.
Oh, yes. So right now, xenon's the big one that everyone uses. SpaceX right now is using argon because argon's more abundant than xenon. Go back to my Cletus design. We did the math. If both of our because we're refueling a Mars transfer vehicle,
Okay.
if the entire combination was refueled using xenon, we'd end up using 50% of the world's xenon production.
Oh!
Yeah. Xenon's very expensive. That's why we should show argon, which is the fourth most abundant element in the atmosphere.
Ah, okay.
It's in light bulbs.
What kind of light bulbs?
Incandescents. So like your standard incandescent light bulb actually has argon in it because it doesn't oxidize things. It's a
Okay.
noble gas.
Ah, yes, all of the commonly used incandescent light bulbs that are definitely now still in circulation.
It's used in other things. SpaceX used to use krypton, so they used like Superman, I guess.
Hmm.
Yeah. So
Well, really trying to become Lex Luthor there, huh?
yeah, Elon found the cave made of crystals, that Superman lived in, and he dug
Yeah.
a tunnel under it and took all of them. That's what the Boring Company was really for.
Ah, got it.
Yeah.
Got it.
So you got mercury. We don't use mercury anymore, for obvious reasons.
Because the planet took it?
Yeah, because mercury is toxic.
Got it.
It doesn't like it collects in your bones and makes you go crazy.
The best way to go.
Yeah, iodine, cesium, bismuth, and Teflon I've seen proposed for like a solid ion thruster. Yeah, that's the stuff they put on. That's the stuff they put on like pots and pans to keep it from. Yeah.
I was going to say,
Also, what John Gotti was made of apparently.
who's John? Oh, yeah.
He's a mobster. Yeah, the mobster played by John Travolta in that awful movie. And I've seen others been pros. Yeah. So this is what it looks like. This is actually the Deep Space One ion thruster firing. So that's a gridded ion thrust right there. So there's ion thruster. There's ions going out. They're happy. And then we've got the little cathode shooting in electrons.
Okay.
Right in there. This isn't a vacuum
Looks like a
chamber.
projector.
It does.
Yeah.
It's projecting ions really fast.
Ah, okay. Yeah.
All right, so a bit more history here. So, yeah, ion thrusters first showed up theoretically when Tsiolkovsky came up with them during the rocket equation, right? In 1904-ish. The first working ion engine was built in 1959 by Harold Kaufman at NASA Lewis, which is now Glenn Research Center. This isn't him. This is a different guy.
Oh.
So
Just some random guy.
Yeah, this is a guy. This is the guy who designed this one and put it all together.
Oh.
Yeah. So Space Electric Rocket Test (SERT-1) carried a mercury ion thruster. There's my spelling mistake. On a suborbital trajectory where it fired for 31 minutes on July 20th, 1964. So that's this. This whole
Okay.
thing. Yeah. So the way you could tell it was working is because they're mounted, so gas will come out this way and this way.
Oh, so it'll spin.
Yeah, it'll spin. That's how you know it's working.
Ah. Okay.
Yep. It was
How do
fired
you-
on- What?
How did they measure that it was spinning? Was that like telemetry data they're transmitting back?
Yeah, there's probably some accelerometers in here somewhere.
Yeah, that's a big battery it's got.
Oh yeah, well it's got part of these little mercury ion thrusters, right?
Oh yeah.
And these are also
yeah.
gridded ions, as you can see. The little,
With the little grids.
Yep, there's the grids, and there's that. So it fired for 31 minutes, worked perfectly. Then there was SERT-2, which was launched on February 3rd, 1970, to a polar orbit, where it fired 2 mercury thrusters for 2,011 and 3,781 hours in space, respectively.
Okay.
They also turned the engines on and off for 300 times.
Dang.
Yeah. The Soviet Union developed their own Hall effect thrusters. So those are the ones where you can see them, and then there's another it's like a ring of cool glowing ion thruster engine, and then there's another thing in the middle that's solid. Those are Hall effect.
Okay.
They use magnetic fields to accelerate it out instead of electrostatic fields. So instead of
Okay.
using voltage, they use a magnetic field to just throw it out.
Okay.
They built their
I
own.
think I understand the difference.
What?
I think I understand the difference.
Yeah, I don't really understand the difference much either. I did these.
You can find like diagrams to visually showcase
No,
the different ones.
I was really excited about the raw data I got on this mission that I didn't really go too deep into the differences of ion thrusters.
Ah, okay.
Do you want me to? I'll untie you and then I'll go find more information. How's that sound?
That sounds good.
Yeah. So the Soviet Union also developed their own Hall effect thrusters that they use on their like geostationary satellites. I think they like launched 100 to 200 of them on their own.
Just because?
Yeah, we never really used them, but they did because of course they did.
Oh.
Yeah.
Of course. Okay.
The Soviet Union just randomly build things. It will fly.
So yeah, good to build the ion thruster today. Launch in space. See where it goes.
Yeah. All right. So this is our mission, Deep Space One.
Ah,
So
okay. Right.
This is a new millennium mission. So we got 2000 is coming around the corner. NASA's trying to do new things. So it's meant to test technologies with the goal of making future science missions lower cost and increase their autonomy.
Okay.
That makes sense to you, right? They gotta make them cheaper, but they gotta do things on their own, right? They're growing up.
Yeah, they're going to be going off to college soon, and they
Yeah.
got to learn how to balance their own budgets.
Yeah. So right, we're talking about. So what these are. So this one is a high risk and low cost mission at $152 million.
That's low cost.
Yes, it is compared to again, like Perseverance is like $2 billion. The Mars rover.
Jeez.
Yeah.
Oh, man.
This is a drop in the puddle. What we're talking about, right? So this is paving the way for the faster, better, cheaper mindset of space missions.
Of which you can only do 2 of the 3.
Yes. So
Yeah.
on this mission are 12 technologies that they're going to demonstrate. 1,
Okay.
the N-star ion thruster.
Oh, the thing we're talking about.
Yeah. The Scarlet concentrated solar arrays.
Ah, okay.
Autonomous navigation. The remote agent. Beacon monitor.
What's the remote agent?
We'll get there.
Are they like 007?
Yeah. With a TV. Yeah. It's like,
Look here, Mr. Bond, a simple television.
Yes. Hundreds of channels, yet nothing to watch. Amazing technology.
If you use the dial on this television and type in like SOS with it or something,
Yeah.
it'll set off a bomb.
So we got beacon monitor operations, miniature integrated camera spectrometer, MICUS,
Okay.
plasma experiment for planetary exploration, PP, Pepe. Oh no, wait, Pepe.
PP.
That's racism now, isn't it? I don't know.
I have no idea.
it's
I
the
haven't kept
it's
up
the
with
frog
meme
that
culture.
people say is racist. I don't know.
How do they determine that?
I don't know. I don't care.
Okay, we'll just go with PP then.
Yeah,
Because
PP.
that's funnier.
Yeah, PP.
PP.
Then you got the small deep space transponder, which I think.
Okay.
Yep. The Ka band solid state power amplifier, low power electronics, multifunctional structure, power activation, and switching module.
So a bunch of nerd stuff.
Oh, nerd things. Yeah, I read.
Come on, son. Let me tell you about radio.
Yeah, I read all the end of mission reports for this thing for every one of these experiments, and most of them are just nerd things. They're not interesting.
That
Unless you
sounded
really like
real
controls.
exciting.
Oh yeah, don't worry. I put a link to all this in the description, of course, so you can suffer if you want.
Yay.
Okay, so this is our spacecraft. This is what it looks like, all folded up. Okay, so these are 2 views of it. So it's 1.5 meters. I'm 1.78. You're, how tall are you? You're about 1.77.
I'm 5 feet 9 inches.
So you're like 1.76.
Okay.
Yeah. Okay, so we
So
got
I could take this in a fight.
yeah.
Okay.
It only weighs like a ton. You can fight it.
Yeah. Like half my weight.
All right, so
Fight it.
we got some things here. So we'll start from bottom up, right? So here's the adapter. So this
Why
is where,
bottom up?
I don't know.
Why not top right?
Okay,
Like
okay, let's go fine, we'll-
clockwise.
No, okay, we're gonna go on this quadrant right here. Okay, so this is the camera, right? This is the camera. You can see it's got
This is the camera.
That's the
Right,
camera.
Say hi to the camera.
So
Don't
over
look at the
here
camera.
then is a battery. Okay, but
Alright.
we'll go with this. We'll keep going on. Okay, so we got the solar arrays, obviously. Star tracker. That's a navigational thing, right?
To track the stars?
Yeah. Once you know, right, it's like, oh, that's these stars. This is where I'm pointing.
So using the ye olde method of navigation,
Yeah.
just with $152 million as opposed to 6 doubloons.
Yeah. So this is inertial management unit. That's part of orientation, steering, that kind of thing. Multifunctional structure. That's one of our experiments. That's the launch adapter and propulsion modules. This is where the ion engine is. This is ion propulsion system diagnostics. So this is the doctors that make sure it's working right.
They do like checkups and perform surgeries and everything.
And then it calls it a moron.
Cool. Yeah, here's your $152 million doctor's bill.
Yeah. You have the integrated electronics module right there. So that's, they put some electronics in there, did calculus with it.
Some integrated stuff, yeah.
Power distribution unit. So that's, sharing the power, man.
That's the distributor.
Yeah. I got some high voltage power unit. Okay. Mike has sunshades. Got I don't want to blind it. Got some sunglasses.
It's got some of those aviators.
Yeah. There's a mustache on here somewhere. I got a high gain antenna, low gain antennas, Ka band antenna. That's another one of the experiments. So these are the antennas right here, right?
Okay.
You got a diplexer. What in the world is that?
That's my question.
That's an electronics thing. That sounds cool.
Not to be confused with a monoplexer or a trioplexer? Trioplexer?
I don't know.
Triplexer?
Yeah, waveguide transfer switches. Now that sounds like communications antenna stuff.
Yeah.
Yeah, so there's PP right there.
PP.
There's the PP.
There's PP.
So these are the sun sensors. This is part of the tracking, right? The orientation. The sun's the really bright thing.
Oh, okay.
Yeah.
The one big star. Got it.
Then here's the battery, which is a bunch of jars. Like in Breaking Bad when they built the battery to restart the RV. So it's a whole bunch of jars
with the wire. Yeah.
Yeah, so it's got a bunch of change and sponge and lemon juice in it. That's what's powering the spacecraft here. I mean, faster, better, cheaper. Am I right?
Yeah.
I got the
definitely do all three of those.
Yeah, you got the service boom. I don't know what that.
Somebody say boom.
Yeah. You got the xenon feed system panel.
Okay, I was about to ask who G is, but
yeah.
So
that's our spacecraft. So this is what it looks like in real life. Right?
Oh,
so
it's very gold.
Oh yeah, it's all wrapped in the nice mylar, Kapton, whatever it's called. I can't remember the word for it now. Yeah, so these are the Scarlet solar arrays, right? They're all packed. They have the protective covers.
They don't look very scarlet, I'm going to be honest.
Well, that's just the name.
Oh.
Yeah. So this is ion thruster, right? So this is N-star ion thruster. The ISP is 1950 to 3000 seconds. The thrust is 20 to 92 millinewtons, which is 0.0045 to 0.0207 pounds force. To put it in perspective, a sneeze is 0.4 pounds of thrust.
So it's 100th the force of a sneeze.
Yes.
Dang.
Yeah. So Scarlet solar arrays, if you remember, we saw them last on Comet where they got blown up.
Nice.
Yep, so using special lens shapes to them, they'll concentrate solar energy onto the solar panels, like a magnifying glass on ants.
Got it.
Yeah.
Is it going to burn the hole in them?
Hopefully not.
Oh.
Well, if there's any ants on it, they won't do well.
Yeah. Well, I mean, ants don't really do any well at all at NASA.
Yeah. So this
It's a massive conspiracy, I say. They hate ants.
That's the real conspiracy with NASA.
Mm-hmm. Earth is spherical, no one cares about the flat Earth. But the ants,
Absolutely.
There's something there.
Absolutely.
They're
So this
hiding
is the spacecraft being integrated. So there's the batteries, of course, right? There's batteries.
Okay.
There's PP. There's a high gain antenna.
PP.
There's some Tupperware over another piece of the equipment.
Why do all of these people look like they're about to be transported by Willy Wonka's machine into, like, the television?
It's a clean room.
Oh, okay.
They need to be clean.
Right.
So that's the first two technologies, okay? So number 3 is called AutoNav. So it uses the positions of 250 asteroids and 250,000 stars to ascertain the spacecraft's position and administer small trajectory changes using the ion thruster and the hydrazine thrusters on board. So there's some classical propulsion on this. I don't know where the thrusters are. They're somewhere. The remote agent, that's James Bond with a TV. This makes decisions regarding spacecraft operations based on the condition and mission goals. It's like HAL 9000, but not HAL 9000.
Yeah, it's James Bond. And James Bond, when Q says, please bring all of this equipment back in working order, and he just destroys it.
He destroys all of it, yeah. So
Yeah.
number 5 is beacon monitor. So this is a simple signal method of determining spacecraft status that doesn't put much strain on the Deep Space Network, right? Contour had this. New Horizons had this, right? It's a way of saying, hey, I'm fine. Hey, something's wrong, but I fixed it. Hey, something's wrong. You should take a look at this and help.
Oh, so it's a way for NASA to ask how is the probe doing?
Yeah,
as opposed to what is it doing?
Yeah, so it's like, you up, right? And it goes, yeah or no, versus it writes a long, lengthy letter saying, how are you, my dearest, right?
Yes.
So number 6 is the miniature integrated camera spectrometer, MICUS. So that's this right here. That's the camera, and that's what it looks like on the inside.
Whole bunch of mirrors and lines and crap.
Yep, it's got some CCDs, IR spectrometers, A1 mirrors. Those means it's good, right? Got some grating UV detector. So it's experiments with 2 visible imaging channels, an ultraviolet imaging spectrometer, and an infrared imaging spectrometer, designed to return imaging data for both scientific purposes and also for use by the autonomous navigation test. Right, you can take pictures, you can look at things.
Right.
You can tell you where it is.
Okay.
Also,
like,
it's also,
hey, look at me.
Yeah,
so it's taking a selfie, basically.
Yeah. Well, no, it's looking at the stars and saying, okay, where am I?
Oh, dang.
It's kind of like whenever I go to an airport, I text a picture of the carpet to our uncle and say, where am I? Right? You try to make him guess.
Yeah.
It's also going to test out lightweight imaging technology, right? You're testing this stuff. It's not really a science mission, it's a technology mission.
Oh, okay. Yeah. So the lightweight imaging, because they're trying to relieve the great pixel shortage from the mid '90s.
Yeah.
And so they're going with lightweight technology to help cut down on the amount of material you need, as opposed to all those heavy pixels.
Yeah.
That really help to fundamentally destroy the pixel economy.
Yeah. Why do you think Galileo was delayed so much? Right? It wasn't.
Right. It's because they just did not have the pixels.
Yeah. So number 7 is the Plasma Experiment for Planetary Exploration, PP.
The PP.
Yeah. A multiple instrument package designed to measure the 3-dimensional mass-resolved plasma distribution. This sounds like something out of Star Trek now. This is just Star Trek, okay?
Yeah, data. Resolve the plasma distribution.
Yeah. Well, I've been watching more Voyager, so it's Tuvok.
Oh.
Tuvok's
Dang. Why didn't we make a Deep Space Nine reference? It's right there.
I don't know.
I don't really watch Deep Space Nine.
That's my problem, too. I don't know. The Ferengi have something to do with this?
I don't know.
Oh, no,
Cisco.
it's Miles O'Brien. He's the engineer on Deep Space Nine. Let's make a Miles O'Brien joke. I don't know any. I don't watch Deep Space Nine.
Either.
The only few episodes I've seen are the one with the Tribbles, the one where the Ferengi end up in the 1940s, the one where the best episode of the show in Pale Moonlight, that one, and then the one where Cisco is a 1950s science fiction author. Those are the only episodes I've seen.
That's pretty bad. I aside from the Pale Blue Moon one, I haven't really seen much of any of them. I've seen the Tribbles one, though.
Yeah.
Yeah, that's pretty good.
That's about it. Yeah, okay. So it's going to measure some plasma, which is cool, I guess. The sun gives off plasma. It's in our TVs, right?
What kind of tape measure do they have for that?
Well, this is the tape measure right here, as you can see. This also looks like something out of Star Trek, doesn't it?
This looks like a time bomb.
Yeah.
This looks like something our inventive hero creates at the beginning of the movie to help revolutionize the energy production that the bad guys steal and add something into it to make it into a bomb.
And it's got these cool glowing bars that go, top down, right?
Oh yeah.
Kind of like the warp core on Enterprise D, right?
Yep. As opposed to what's the one ship from Deep Space Nine? The Defiant.
Yeah. Yeah. Okay, so what it's going to do is it's going to use to collect scientific data during cruise and asteroid encounter, measure the effects induced by the ion propulsion system on the space environment, including interactions with the solar wind and on spacecraft surfaces and instruments, right? You're firing engines out of the back of your spaceship that's charged electrons and charged, particles. How did that interfere with your spacecraft?
Yeah, how's that going to backfire?
Yeah, anything going to go wrong, right? And validate new plasma sensor technologies for use on future space flights, right?
Basically say like, hey, this thing actually works, so let's keep using it.
Yeah. So number 8 is the small deep space transponder, a smaller version of a communication system, and it was built by Motorola.
Wow.
Yeah.
They built everything.
Yeah, they don't exist anymore, really.
Yeah.
Yeah. Number
Good
9.
job, Motorola.
Yeah. So number 9 is the Ka band solid state amplifier. So of course, right, I talked about Ku, the K under band or K upper.
Mm-hmm.
So this is Ka. So they want to use this because it's actually easier to transmit data with. The one problem with it is that water absorbs it way better.
Oh, so if there's any cloud cover,
Yeah,
it's just worthless.
Yeah.
You're speaking to the clouds.
Yeah. So they're testing that. Oh, also this is what PP looks like. Right size. It's the right size of it. Yeah.
That's huge. Look at that thing.
Yeah. So then number 10 is low power electronics. Experiment involves low voltage technologies, low activity logic, low energy architectures, and micro power management. Right? It's
Nerd optimization.
It's electronics that don't use as much power.
Got
So
it.
you don't need as big of batteries, you don't need as big of solar arrays, which costs less.
Right.
Device-
Because it's just you have less of it.
So devices tested include... This is just ripped from the press release, by the way. This is why I copied this from. I was like, I'm not going to paraphrase this. Devices being tested include a ring oscillator, transistors, and multiplier, and are designed to consume very little electrical power, right?
That probably excited like an electrical engineer, right? They're probably like, "Oh yeah, I know what that is.
Yeah,
I know
so
how that could
cool.
work."
Yeah.
And then like everyone else is just like, "Okay, those are words, I guess."
Yeah, that's cool. Words.
Yeah, look at those words. A transistor.
Ah, yes. Multiplier. Ooh.
Yeah, I too watch Markiplier occasionally.
I don't, because I outgrew that. But so
Yes.
number 11 is the multifunctional structure. Combines thermal management and electronics into one load-bearing structural element. So instead of it being, okay, we got our gimbals, we got this, and they put them all together inside this honeycomb thing, it's like, no, we'll put them all together on one thing.
They just
Yeah.
make it
Yeah.
one structure.
Yeah. So number 12 is the power activation and switching module. It's a smart power switch. That's what I used. That's my phrasing of it. Yeah, it's just a way of testing out power systems, I guess. Why are you looking like this?
Hilarious.
It is. So also right here, this guy's mixtape, right? So that's it's got the names of all the Kennedy Space Center workers. So they put that in, I think, like right about there on the spacecraft.
They just shove it in.
Yeah, they taped it in.
So they got a CD player on this thing?
No.
Oh. Where's the
Yeah.
aux port?
I don't know. That's deep space too.
Ah, okay.
So-
they finally got their stuff together.
So the other thing on this mission is this spacecraft right here. You can see it.
That's a spacecraft? It looks like a box.
It is a box. Well, most satellites are just boxes.
Oh, okay.
Yeah.
Oh, yeah, because made by engineers.
Yeah. You think
Build
maybe
a box. Put the stuff in the box. It's simple.
Yeah.
What do you need?
Yeah. So this is the students for the exploration and development of space satellite 1. It's an amateur radio satellite. That's pretty much all it's doing.
Okay. Got
It
it.
got deployed into low Earth orbit. All right, so
Just
this
chucked
is
out there.
so this is rocket assembly. I figured we should show some pictures of this being done because I think it looks cool.
Ooh.
So this is how the Delta II is built. And you've
Dang.
seen one of these. This is right by the Air Force Space Museum that we went to at Cape Canaveral.
Okay.
Yeah, so this is where they build them up, right? So they take the extended long tank Thor. That's what this is,
Okay.
and then they stack it up right on here,
Mhm.
and I guess they just roll it out to sunbathe, and then they put the solids up in here and mount them, and then roll it back in, and then mount the solids onto that way.
Okay. So they put the rocket up, then put on the solid
Yeah.
boosters, and then put it back out.
I see no reason why this costs so much.
Yeah. No, that sounds like a very cheap method.
Yeah. Yeah. Yeah, so this is built up with the Delta, and you can see here it is in the assembly building, right?
Mm-hmm.
Right, it's right on top there.
Okay.
Yep.
Yeah, and they're just loaded up in the payload fairings.
Yep, so kind of put the payload fairings on. I think, where's the other one? It must be behind here.
Or somewhere else.
You can see how kind of big and small the spacecraft is.
Yeah, it's a pretty large room, but it's also very cramped.
Yeah.
That's weird.
Yeah. All right, so this is the mission plan. This is the original one. So they launched from Earth, right? Here. Oh, this is the
Oh.
sun, wait. And we're drawn differently, don't worry.
Thank you. Consistently inconsistent.
Yep. It's a pretty fat sun. So they're gonna launch it, gonna test out the engine, they're gonna fire it, they're gonna bit, and they'll pulse it, and they'll do a flyby of, I think, the asteroid McAuliffe, which of course is named for Krista McAuliffe, who died on Challenger.
Okay.
And then they'll do another flyby of the comet. Oh, I forgot the name of the comet. They're not going to fly by it, just so we're clear. It's the original mission plan. It's
Okay.
like Wind Kahutek Iverson or something like that. And then that'll be it. That's a bonus. The real mission is to just turn on the ion engine. Does this work? We thrust it for a little bit. And then maybe we'll fly by an asteroid if it works really well.
Okay.
That got delayed to October 1998. So the new mission plan then is to launch on October 24th, 1998. So the solid lines here are when they have the ion thruster on, burning continuously.
Oh.
Yeah. We're going to burn
And so
this
the
thing.
dotted lines are just where it's coasting?
Yeah.
Oh.
So then they'll do a flyby of the asteroid 1992 KD,
Okay.
right? They'll rendezvous with that in July 1999.
Okay.
And then they'll see if they can fly by the comet Wilson-Harrington. And then,
Okay.
if they're lucky, they'll do a flyby of the comet Borrelly.
Borley.
Yeah. Same for a French guy who discovered it in 1904.
I don't believe that simply because the name, you pronounce all of the letters.
Oh.
Sure is French.
Yeah.
Okay.
Well, then again, I could also be pronouncing it wrong. I haven't heard it spoken.
Nah.
So I could be
that's
saying
okay.
it wrong.
Yeah, it's actually pronounced Bor.
Yeah.
And the rest of the letters are just there for.
Give me a second. I gotta draw the sun. I am drawing it differently.
You see, right?
This is terrible. Now it's got a nose.
Yeah. Now the actual sun is the nose.
Yep. So you can see, so it's gonna be a quick 2-3 year mission, right? Launch in late '98, and then if they're
Quick 2-year mission in and out.
yeah, quick, in, get on with it, get it over with, get out, get it.
Got it.
Good. All right, so it launches on October
Oh,
24th,
wow.
1998 at 8:08 in the morning Eastern Daylight Time. Look at that launch.
Oh,
Isn't that a
that's
pretty launch?
beautiful.
Yeah.
It's pretty.
So this is a
Yeah.
Delta II 7326-9.5. Don't worry about the nomenclature. So that means it's a Delta II with 3 solid rocket motors. You can see those,
Mm-hmm.
right? And then a Star 37 FM third stage, which we saw in the vehicle integration, right?
Yeah. Right. Yep.
So at 9:01 in the morning, so
Mm-hmm.
about an hour later, the third stage, the solid motor, burned to kick it on a solar trajectory. So it's going to fly out of the Earth-Moon system around the sun.
Okay.
Telemetry was received by the Deep Space Network 1 hour and 37 minutes after launch, 13 minutes later than intended. We don't know why.
Oh, so it's just late to send the email back?
Yeah.
Huh.
Maybe it's got social anxiety. Maybe it's like me.
Yeah, I always freak out with emails.
I keep forgetting to reply to emails all the time.
It's like, I'll reply to it later when I'm feeling more confident, and then just that never
Well, then,
just
yeah,
happens.
it's 2 days later. It's, oh, this is kind of embarrassing now, isn't it?
Yeah, that was too late. Okay, might as well
Yeah,
wait.
so the
Just
ion,
never reply.
So then they turned on the ion engine, and then it promptly failed 4.5 minutes into later.
Uh-oh.
So what happened was, the most likely answer is that some debris from the Delta II got caught in the gridded part of it, right? Because remember, it's basically a gap, right, of high positive voltage and high negative voltage.
Okay.
So something probably got stuck in there and just shorted it,
Oh.
right? So pretty much what they did is turn the engine on and off a lot, and it got rid of the problem. Yeah. So then,
Wow.
this is when they started doing almost all the experimentation and testing of all the systems. I'm not going to describe any of it because it's boring. It's dumb
Right.
nerd stuff. Okay.
I mean, yeah, it's basically just regular IT stuff, right?
Yeah.
First, you turn it on and off again, see if that works, and then when that finally does work, then you can go through and check all the rest of it.
Yeah. But now it's en route to Comet 1992 KD. Now again, I want to emphasize not Comet, Asteroid. The Asteroid flyby, anything after that, that's just a bonus. Most of the stuff was done within 3 months.
Okay.
But you got the thing up. It's $152 million. You're gonna get the most bang for your buck.
Yeah.
So, it's Asteroid. The asteroid is named 9969 Braille for the language for blind people.
Right. I mean, after looking at this image, I think I'm going to need Braille.
It is ironic that the one that... So, the original plan was to fly within 250 meters of it, so about 700 feet.
Oh, wow.
Yeah,
That's
we'll
close.
talk about this. So, So this is 9969 Braille.
Mm-hmm.
Blurry. So
Very.
the aphelion, so the farthest away from the sun, is 3.3557 AU, and perihelion's at 1.3263 AU. So it's outside Earth's orbit. I think it's a Mars crosser.
Yeah, probably.
Yeah. So its orbit is 3.58 years. So 3.5 years. You have a handful of birthdays and then you die. So it's about 2 kilometers long, right? 2 kilometers, and then it's 1 by 1. It's a potato.
Okay.
That's why I made note of it there.
Right.
It's a potato. It's considered a V-type asteroid, so it's kind of like the asteroid Vesta, but now it's suspected to be a Q-type, tying back into Star Trek Deep Space Nine. Does Q appear in Deep Space? Well, no, you wouldn't know. I've seen more episodes.
I don't know.
I don't know.
Is Q in Deep Space Nine? I don't know. I thought it was just in.
He's in Next Gen. He does show up in Voyager.
It's maybe in Deep Space Nine.
I don't know. Okay. So Deep Space One did an encounter of Braille on July 29th, 1999. It does a flyby of 26 kilometers at 12:46 in the morning Eastern Daylight Time. So you get to crack up, you're waking up really early in the morning to do the flyby. What's all this early morning stuff with all these space missions?
Yeah, I don't know. It's poorly timed for. I mean, was space invented by morning people? Because that's the only explanation I can think of.
Yeah,
because if it was like
Konstantin Tsiolkovsky was a morning person, and we have to suffer for this.
That explains it.
Yeah,
unbelievable.
So
if it was up to me, it'd all take place in the afternoon.
Yeah, because even Osiris-Rex tomorrow morning at 9 a.m. Central. Ugh. So the flyby is a partial success. So the day before, the spacecraft suffered a software crash. so they had to change the trajectory so it didn't hit it. just because the system crashed. You got to modify your systems. So it was supposed to be, again, 240 meters. That would have been really close.
Mm-hmm.
Now it's 26 kilometers. It's blurry. So then the mic has also failed. It only took 8 pictures. This is one of them. And again, I want to emphasize, this is raw image. I downloaded. So, I knew I forgot to bring up something. So one of the links here in the description has access to the raw data from Deep Space One.
Mm-hmm.
This is in one of those files. You can even find a little animation they made of Braille and then the next thing they encounter. You can find images. You can find the raw data from this mission. I'll warn you, it's all in ancient file styles. It's in dot labels and dot caps.
It's in hieroglyphics. You need the Rosetta Stone to figure it out, huh?
Oh my god. That's what it felt like. And this image, of course, so I had to go through GIMP because the image file that you can get is .img. The problem is, in modern computers, .img means disk image, like your hard drive.
Oh.
So every time I wanted to open up a picture, it said, "What are you doing, buddy? Why are you trying to get into this stuff?" So I had to tell
cease your investigations.
Exactly. So I had to tell it, no, open up GIMP so I can export it as a PNG to put in here.
Okay.
Yeah. So they had a software crash, so he does a flyby of 26 kilometers. I guess. The ultraviolet spectrometer had failed by this point, I guess. Boring. So following the flyby, Deep Space One completed its primary mission on September 18th, 1999, with resounding success. Everything worked perfectly. It was great.
Yeah. Hey, good job. Yeah, we had some of the blurriest images ever to grace the internet, but
it's fitting though. It's Braille. So by then they'd used 22 kilograms of xenon, which is about 1.3 kilometers a second delta V.
Okay,
that's a lot. An extended mission to the dormant comet Wilson-Harrington and comet Borrelly in 2001 then began.
2001, a space odyssey.
Yep. So then, this is.
Wait, that's the Loch Ness monster.
That's Nessie, all right. Okay, so this is Borrelly, comet 19P. That's how he tells a comet. It's number P.
Number P.
Here's the thing, though. Okay. On November 11th, 1999, the Star Tracker failed.
Uh-oh.
The off-the-shelf component that everyone else was using broke. The experimental stuff worked fine.
So what's the one Mark Twain quote that The Big Short starts out with? It ain't It ain't what you don't know that gets you. It's what you know that just ain't so.
Yeah. So what they did is they took Micus and used that as a replacement for the star tracker. Because it's got 250 asteroids, or 250 stars and 250,000 asteroids, so it's a navigation system. You combine that with AutoNav, and you can read about this, all the nerd stuff, if you really want to, in the description. And so what they did is they used that to navigate.
MacGyvered it.
Yeah, with duct tape,
Okay, they MacGyvered.
bubble gum,
Nice.
and hair. I mean, you remember MacGyver? He had, it was a mullet. Yeah, he had some hair. The one problem is that Micus has a severely limited range of view, severely constrains the trajectory and design. So they actually abandoned the Wilson-Harrington encounter in favor of a September 2001 encounter of Borrelly.
Oh, was that also on the 11th of September?
No, 22nd.
Okay,
So
good.
what I'm not going to talk about here, of course, are the efforts and trajectory corrections made in support of using Micus, including some delays caused by terrorist attacks, to ensure the correct encounter with the comet.
The whole 9/11 happening.
Yes. So this is 19p Borrelly. This is a raw image from Micus. This is a raw image from about 2,000 kilometers away. So
Got it.
Borrelly.
So wait a second. Why was the one image from 26 kilometers away so blurry, but this one from 2,000 kilometers away so well defined in comparison?
Because Micus didn't work during the Borrelly encounter.
Okay.
Micus worked on this counter. Braille, it didn't work.
Got it.
Yeah, because of the software crash, I think. Something like that.
Right.
Yeah. So Borrelly is a comet that has an aphelion of 5.9 AU, so that's like Jupiter. Or out
Yeah, it's past Jupiter.
And then its perihelion is 1.306 AU, so it's outside Earth's orbit, but kind of close to Braille, right?
Right.
The
Yeah.
orbit is 6.85 years, so, not many birthdays. And then this one is 8 kilometers by 4 by 4 kilometers. It's a potato.
So another potato.
Yes.
Okay.
So Deep Space One performs a 2,171 kilometer flyby of the comet on September 22nd at 6:29 p.m. Eastern Time. So someone sane took over at this point.
Yeah.
They got their supper out and they're like, okay, we're going to fly by the comet now.
Yes.
And sent back these pictures. It took a lot more.
Good.
So this is Borrelly.
Ooh.
Yeah.
Looks like a bowling pin.
It kind of does. So this is what Borrelly looks like up close. Well, up close, 2,000 kilometers away.
Yeah, up close and personal from
Yeah.
2,000 kilometers away.
So you notice, it's noted in the reports, like there's certain jets coming out of certain areas. You got, again, this is a comet. This is what comets look like up close.
Very potato shaped.
Yeah. So this is another image. This is one of the jets that they took a picture of. And I want to emphasize, this is raw images. I found these. This is cool.
Okay.
This is a map of the surface of Borrelly taken from radar, they don't have radar on board, from the camera system on board. They can kind of guess the altitude of certain parts. You can kind of see it's got little mountains. The resolution's not very good.
Yeah.
You can see, so it's by kilometers, by meters. Sorry. I actually did have the raw data for this. I was going to put it in Excel because it's at XYZ coordinates of everything. The problem is it's 62,838 points of data. I tried to do that in Excel. Excel then went, I'm not doing that, and then killed itself.
Oh.
The fun part was I turned Excel back on and I said, okay, I'm not going to do that. I'll tell it not to do that. It opened up and said, what was I doing again? Oh, right, this. Dead. So, I was hoping to make one that make it look like fit with our chart style, but that just didn't work out. But this is what Borrelly, the surface of Borrelly looks like from. This is coming in from the south and the underside, so it's flying under it.
Okay.
Yeah, this is half of Borrelly.
So the underside is very, very rough.
Yeah, and the other side, look at that, it's just flat, like Earth,
Just flat.
just like Earth. Yeah.
Perfectly flat.
So now the other thing, this is other raw data I got, is so this is the diagnostic system of the ion thruster, right? So that's the ion thruster. You got the RSU that does something. The DCIU.
Roy State University. I don't know.
Yeah, this is the DCIU. That's a medical thing. So this is the diagnostics package for the ion thruster, which was turned off during the flyby. But
Okay.
it's an ion thruster diagnostics package. It can measure electrical things, electromagnetism, like this.
Ooh.
So this is raw data from 3 channels of the 24-channel ion thruster diagnostics package. Now I think this is the electromagnetic field density. I should have written down what these were. Because it's more Star Trek stuff.
All right.
So you can kind of see when we hit the comet, right?
Right, kind of that peak.
Yep. This is the comet encounter, and so this is in decibels per microvolt per meter.
Okay. I'm no doctor, but I don't think the heart is supposed to be doing that.
Yeah.
It's just
yeah.
It's just dancing.
You should probably go see a medical professional if this is happening to you.
You should probably go see a real licensed doctor if that's happening.
So this is data from that. So here's another chart. This is the field density from three of the channels, I think. This is microvolts per meter per square root of hertz. I really should have written this down, what these were, what these meant.
Yeah, they're the results of this thing that I have no understanding
I don't know what it means.
of.
Wouldn't it look nice?
Yeah, nice graph. What does it mean?
Don't know. I'm an engineer. I don't know what any of this stuff means. It's science. It's nerd things, okay? Gosh. So you can see there's a nice peak. So the thing they did notice was that the magnetic tail of the comet was offset from the normal gas and dust tail.
Okay, why was that?
I don't know. I'm not a science person. I finished these.
So I guess some stuff happened.
I finished these slides a week ago.
Yeah, you had a whole week then to figure this out, and you didn't bother?
I've been working on the slides for the next episode.
Okay. Please tell me you're going to go back and make sure that you write all this stuff down next time. Then,
so
right?
So for the next episode, I'll talk about the Deep Space One results again. Gosh.
As opposed to talking about them in this episode, in which we're actually talking about the Deep Space One.
Yeah. So this is. Oh, I didn't change the name of the series. Oops. So this is the magnetic field density. That's what this is, because it's picoteslas per square root of hertz.
Are you sure?
Yes, I'm absolutely sure.
Okay.
From 3 different channels. So you can see when you encounter the comet, right? And you can see that it's a bit offset from the nucleus.
Okay.
So, yeah. Isn't that cool? This is raw data. I processed this in Excel.
I think, yeah, you think you're a little too fixated on the fact that it's raw data that you ignored the actual data.
What it actually means? Oh.
Yeah.
Oh. I was just so excited that I found this.
That's good. That's good. I'm glad that you're excited. I would like to know what it means.
So would I. But don't the charts look nice?
Oh, yeah. The patient's dead, but the charts look great.
Yeah. Hey, did you see the surgery I did on him?
He's dead.
You can't appreciate it, but it looks good, okay?
Yeah.
Is that why my medical license got revoked?
No, that was because of the some other reason that I'm too tired to think of a good joke for. I'm sorry.
Well, you should be. The patient's dead.
Yep.
All right.
And we have killed him.
So after Borley, they kept burning the ion engine until they told it to turn off on December 18th, 2001 at 3 p.m. Again, the good person in charge here, so it's on a morning thing.
Yeah. Yeah. Good. That's
so
good.
At this point, the engine had fired for a total of 16,265 hours.
Jeez.
Yeah. I think I have that amount of time on Kerbal Space Program.
That's like 2 years.
Yeah, it's about how much time I have on Kerbal Space Program. And in total, they used 73.4 kilograms of xenon for 4.3 kilometers a second delta V.
So how much is a kilogram? What's that in freedom units?
2 times 2.2. I have my calculator with me. So 73.4. Turn on 73.4 times 2.204. So it's about 162 pounds of xenon. So less than my weight in xenon.
Got it.
Which is really expensive.
Yeah, unlike you. Which is not expensive, I presume.
No, I'm cheap. Okay. And other reasons why my medical license was revoked. So
yeah,
the other thing-
underpricing the body parts.
Yeah, that's true. Yeah. I'm not even a doctor. I just come in here and look at charts.
Judge you for your charts.
Yeah. Is this aesthetically pleasing? The patient's dying.
Yeah, but think about the aesthetic, all right? Think about the doctor experience for a moment, okay? Stop thinking about the patient so much.
Yeah.
Think about me.
And then look at this
The
chart.
doctor.
I can't even read it. That's his signature. That's worse. Doctors have horrible writing. That's the joke.
Yeah, I got it.
Okay, you still awake? So they also turned the engine on 199 times. And it worked every
Should've
time.
turned it on just once more.
Yeah. So there were plans for another mission in 2002, to do another comet flyby or something like that. But at that point, no one was really interested in doing this. The mission was completed already, a year ago. And, by that point, personnel were moving on to bigger, better projects.
Oh, okay.
Also, they lost contact on March 6th, 2002.
Dang.
Yeah. So it's still out there. It's in orbit of the sun.
Just chilling,
Yep.
vibing.
Yeah. You've got the mixtape to listen to the whole time. Oh, no, it's been
Just the list of names.
Yeah. It's been listening to that for over 20 years. I think it's going to be pretty mad at this point.
Yeah, it's insane.
Yeah. So Deep Space One performed perfectly, exceeding the goals set out for it and demonstrating the technologies needed.
Dang.
Yeah. So here's some of the
It's quite the
impact.
achievement.
What?
It's quite the achievement.
It is. So here's another one. So here's a good one. An important one. So this is the Dawn mission. This is the one that went to Ceres and Vesta. Launched in 2006. Do you know what this is? Imagine it without that cover on, you pervert.
Judging by how circular it is, I'm assuming it's some kind of a engine, perhaps?
It is a gridded ion thruster. N-star.
Ah!
Yep.
Why is it in the corner?
They have three of them. So there's one here, there's one
Oh.
here, and there's another one on the other side, kind of angled the same way.
Huh.
Yeah. So Deep Space One proved that low thrust solar electric technologies, paving the way for this mission to Vesta and Ceres. It would not have been cost effective to use chemical propulsion. Because going
Okay.
to Vesta and Ceres requires a lot of delta V. So this mission did that. It succeeded with it.
Nice.
On the mission Deep Impact, the Comet data assisted with designing the impact, and the auto-nav navigation system really helped during the encounter where they bombed an asteroid.
Ah.
Yeah. And then the Deep Space Transponder was used on spacecraft from 2001 to at least 2007, from what I've heard, from what I was reading, and several deep space missions like the 2001 Mars Odyssey, which is still operating. It is the oldest
Nice.
spacecraft orbiting Mars. We still use
Wow.
it.
Oh.
Yeah.
Hey, congratulations.
Yeah.
Long time. That's
Yeah.
nice.
It's been operating since 2001.
It's tired, just wants to go to bed.
Yeah. All right. So what did we learn on this mission? Also, this is the banner that they used for the website back in 2002.
Nice.
You can tell by the pixels.
Yeah, again, the whole pixel shortage. They were developing that light pixel weight
Yeah,
technology.
it was one of the technology demonstrations there. So what did we learn? Again, what did we learn on this mission?
Well, we learned that I'm now going to go blind and have to use Braille after the encounter with Braille and the raw data imagery that you showed me. I learned that you need to focus more on the actual data as opposed to the fact that it is raw data.
The next space probe will I found the data for the next space probe we're going to look at too. It's from the same site.
Awesome. Are you actually going to know
I
what
will-
it means this time?
I will label the chart this time. Also, that's going to be a comet flyby too. That's Vega. It's going to fly by Halley's comet.
Oh,
Yeah,
nice.
it's going to be Soviet though.
Oh. So it's going to be the red comet.
Yes, and their propulsion systems use vodka.
Yeah, how's the ion ability, the ion thrust abilities of vodka?
Well, no, we'll find out. I traded it all
Learned
for
that,
Pepsi.
Yeah. I learned that the people who decided to name the different elements, like I guess the noble gases, they had a lot of fun with them.
Oh yeah.
I also learned that you have electrically powered spacecraft.
You can't use them on
Which was-
Earth though.
Yeah, it sucks.
Again,
But
you'd sneeze with greater. So you get one astronaut then,
yeah,
or
but
all your astronauts just sneeze, and they'll push
Yeah.
the spaceship up.
yeah, exactly. That's how that'll work.
Yeah,
We could just use electrified rail. The train.
a railgun.
Yeah, railgun too.
Actually, a light gas gun does better. Just saying.
Oh, okay.
Yeah. Ooh. Yeah.
Ooh.
Yeah. This is a fun mission. It's a cute little one.
Yeah.
Yeah, we get to learn about ion
And it's
engines to prove that they
You
work.
could just fire an ion engine for like 2 years and use up a corpse's worth of xenon fuel.
Yeah.
Yeah.
Yeah, it's a cool mission. It's a cute little one. Again, we didn't really use ion thrusters. We built a few, tested them in the 60s. It was like, whatever. We didn't use them until the 90s. But the Soviets
It's like,
used
hey,
them.
wait a second. We have this technology. What are we using?
Yeah, the Soviets used them a lot on their own spacecraft. Because again, it's probably because it was the crude and simple solution to whatever they wanted to do. It was either that or take, like, I don't know, throw metal off of the spacecraft to adjust it. I don't know. Just some weird solution that some guy, some Vasily thought of.
Yeah. While Slav squatting in an intellectual form.
Yeah. Yeah. That's Deep Space One. It's a cute little mission. Prequel to Star Trek. It's been a long road.
We're not referencing Star Trek Enterprise.
We're not?
No.
I actually kind of like Enterprise, though.
Yeah, it's kind of fun.
It
But
is.
Deep Space was so good, we got 2 through 9.
Yeah. What happened to those?
Probably some uninteresting things.
Or they all blew up and died based on how Star Trek works. Yeah, the one thing that probably didn't work here was the power panel. It probably just exploded, blew off, and killed a JPL intern somehow. From
somehow.
3 million miles away.
That just happens.
Yeah.
Sometimes.
That's what they do. They don't have fuse boxes in Star Trek. You'd
No,
think
of course.
that
Why
warp
would you have
drives-
fuse boxes?
I don't know. I guess because you don't like your ensigns.
Yeah, well, I mean that's the real dilemma. Either you can have warp technology or you can have fuse boxes. I mean, which would
That's
you
true.
pick?
Yeah, Zephram
Like, come
Cochrane
on.
didn't have them, so we didn't do anything. We didn't change any of the designs from Zephram Cochrane, and it's like, I didn't have fuses, whatever.
Yeah, they didn't have fuse boxes back in his day, and he managed to get start the whole
Okay.
encounter.
Okay, so for our non-Star Trek fans, this is the end of On the next episode, we're going to talk about STS-51F.
Yeah.
What do you think this mission's going to be about?
So let's see, Space Lab 2 and Abort Mode ATO. What does ATO mean?
Abort to orbit.
I was hoping you could say, well, you'll have to find out next time on
Oh.
End of Mission.
Nope, we're not going to do that. Nope.
Oh,
Nope.
oh.
We're not ending it yet. So,
Dang it.
Kind of do like the final custodial things.
Oh, right.
Yeah, so it's going to be a really exciting mission. Also, I really have to do a lot of research on this one because there's about 3 exciting things on it.
Okay.
It's a lot of science. Again, Space Lab is not satellite deployment. Where you can just say,
Right.
this went to geostationary and it was fun. No. We're doing some science.
We're doing science.
A lot of
We're doing
diagrams.
science.
Yeah. Also, a bit of the Cola Wars, but again,
For the what?
the Cola Wars. We'll talk about that.
Okay.
Yeah. So that's going to be the next episode, the STS-51F. That one actually launched in 1985 to go and coincide with its numbering, not like STS-51A, which launched in 1984.
Yeah, I mean, why would they come up with such a bizarre numbering system?
I know,
who would
right?
use it?
Yeah, who would use a horrible numbering system for their numbers of their episodes?
Yeah, that'd just be weird. Just go in numerical order.
Nope. Can't do that.
Nope.
All right. Okay, so for kind of custodial things, obviously, again, like, comment, subscribe. I do mean that. I do like, please do evangelize. Spread the good word of end of mission. I don't know.
Dress up in a nice suit, knock on strangers' doors and ask them, hey, have you heard of the End of Mission podcast?
Yeah. And then when they slam the door in your face, we'll make a little comic for them.
Yeah. Well, yeah. And then we'll just put it in all the bathrooms of all the gas station
And truck stops, yeah.
Yeah.
I actually
truck
did find a
stops,
chick tract at the gas station outside the Arsenal once. wasn't even one of the fun ones. It was one of the boring ones.
Dang it.
Yeah. Yeah, so, like, comment, subscribe, all that. We are doing a live stream on October 28th. Our spooky Halloween stream involving
It's
Left 4 Dead.
super spooky. Ooh.
Yeah, the specter of my inability to spell and to research properly.
There's a specter haunting the End of Mission podcast.
That's me! I died!
He's dead.
Yep. Yeah. Well, it's not October yet. All right.
Oh, yeah.
Okay. So yeah,
Happy September, everyone.
it is September, isn't it?
Yep.
Where in the world? 2 months ago, I was in the Philippines. That was so much nicer.
Yeah.
Hotter, but
Where are you now?
somewhere hot and humid, but not the
Yeah.
Philippines.
Yeah.
That was so
Are you
much.
gonna untie me yet?
No, I'm calling the police. You broke into my house and trespassed.
Ah,
Wait, would
dang
this
it.
qualify as unlawful detainment then and kidnapping because I made you record a podcast with me?
That's what my lawyer's gonna say.
Oh. I guess then we
Yeah.
have to end this then.
Wait, and what?
The podcast.
The
episode.
podcast or me?
The podcast. We're not true crime. I thought about doing true crime, but we'd suck at that.
Okay.
This
yeah.
is a true crime podcast,
Yeah.
obviously.
Can't wait for my JSC episode.
Yeah. We get to listen to psychoanalyze me as it's your interrogation. There's something just wrong with this guy.
There's something wrong with him.
Yeah. We should probably end this because we're just kind of fluffing around now.
Yeah, got the whole Minnesota goodbye going on.
Yeah. All right.
All right then. Well, this has been End of Mission.